All right, everybody. I thought it would be time for one last example, an applied example on U substitution. So what we'll see here is a problem that involves the U substitution technique for integrals, for antiderivatives, but in the context of a bigger problem where there's a story behind it, okay? So it's not a problem where we just calculate something. We have to interpret the information we're given and figure out how to use that with whatever technique would be appropriate to get what we want, all right? So here's the setup for the example. It says that we have a function that gives us the rate of the growth of a population, okay? And that's this function right here. And with any function or any number that measures something, we're always given units, okay? If there's a measurement of something at all, there's got to be units. So it's given that this function measures the rate of the growth of a population, how fast it's growing, but the units are in millions per year. So if this function gave us the number 5, that would mean that the population was growing by 5 million per year, okay, at that time, like whatever time was. All right, so that's what that function does, tells us how fast the population is growing. And then we're given this secondary bit of information that it so happens to be that the population in year 2 is 50,000. Okay, I made a little mistake there. I'm sorry about that. So hold on just a second. Let me correct something. It's 50,000. Okay, it's not 50,000 per year. It's just 50,000. Okay, all right, got that fixed up. So the population year 2 is 50,000. Now, those numbers, that does not mean that if you put 2 into this function, you get 50,000, because what's given right here is not what this function measures. This measures how fast the population is growing. And then this thing right here, this number tells you what the population is. All right, now I say that, I emphasize that because there are those two things to keep in mind. There's how fast the population is growing, like maybe it's growing by 5 million people per year, all right? But then there's a separate issue, a completely different number, is what the population is, okay? So the population could be 5 million, and that's just what it is, or it could be growing by 5 million per year, all right? So I got these two bits of information, and they seem to target different things. Now, all right, here's the question. Part 1 of the question is find the population function. All right, so that seems to be like, can you find the thing that gives you this sort of information? I don't want the function that tells you how fast the population is growing. I want the function that tells you what it is, okay? So like the function might be p of x, and it tells you the population in year x, okay? And then the units would be consistent with this one, and that would be in millions, all right? Now, so let's think for a second. How could we take the function that tells you how fast the population's growing and get the function that tells you what the population is? That's all this part 1 question boils down to. I have a function that tells you how fast the population's growing, and I want the function that tells you what the population is. You see the difference between those two things? Well, there's the connection. If I took the derivative of this one, I don't have this function, but if I did, and if I took the derivative of it, the units would be in the change in this variable, the change in the population, over the change in this other variable, which is time, okay? So what I'm saying is if I took the derivative of this function, it would be this one. It would be the function that tells you how fast the population's growing. Okay, so the function I want is such that if I took the derivative of it, I would get this one. So that's the whole key to figuring out then how to get what I want, how to take the function that tells you how fast the population's growing and get the function that tells you what the population is. So it would be like this. P of x is the antiderivative or indefinite integral, there's a fly in here, of this one, x times e to the negative x squared dx. Okay, so this is how I can do it. Whenever we're trying to solve a math problem, we got to like figure out the method for doing it. So there's the method. And I know that this will work because if I took the derivative of this, it would give me that. And I'm just working backwards. That's what the antiderivative or the indefinite integral does for us. Okay. Now, the next question would be, well, like, how do I calculate it? How do I get the indefinite integral? How do I work this out? So to work this out, we'll use something called substitution, and I've made, I believe at this point, 3 other videos to explain how that's done. But what I would want to do is this. I want to use substitution, and I want to reduce this integral, this indefinite integral, to this one. Now we have some basic formulas that integrals are worked in terms of, and the one that this one is going to become is a basic formula that says e to the power u du has antiderivative e to the power u plus c. Okay? All right. I'll make a u substitution that will reduce this integral to that one. And once I get it to that one, well, then there's my answer. So the way that this integral could be reduced to this one is to make the substitution that u is negative x squared. That part will be the u. You know, it might seem reasonable or obvious that that's how you'd want the substitution to be if this is going to reduce down to that. Okay? Now that's changing out the variable x and putting it in terms of u. The dx, the differential, is something different. And the way that I incorporate that substitution is I take the derivative of both sides of my original substitution. The derivative of u is 1, but it's with respect to the variable u, so we say 1 du. And the derivative of negative x squared is negative 2x dx, okay? Now, notice that I see I have x dx, but I don't see that I have negative 2x dx. So often we have to rearrange the numbers here a little bit and make everything fit up there. So if I take this equation here and I divide by negative 2, it tells me du over negative 2 is x dx. And now notice that everything fits. The goal with the substitution is to take the variable you start with, x, and substitute all the x's and the dx in terms of this new variable u. And we then solve the problem in terms of a basic formula and the variable u. So watch, I'm going to take this substitution, and not that middle one because it wasn't exactly fitting of the equation I had, and that one, and I will put them in this step right here. I will substitute them exactly as they are, and it will turn this into negative 1/2 e to the power u du. Okay, because I put u in for negative x squared, e to the u. For x dx, I'll put du over negative 2, but that's a constant which I factor out. That negative 2 under the bar turns out to be the number negative 1 over 2. All right? Okay, so then now I've got a formula for this. The antiderivative of e to the power u du is e to the power u plus c. So here it is. It's negative 1/2 e to the power u plus c. There's my answer. Now, the variable u I used just to solve this integral. The original variable x is how I want to express my answer. So here's how I'm going to get it. The function that measures the population is going to be p of x is negative 1/2 e, and the substitution I was using, which is still valid now, is u is negative x squared. So negative x squared plus c. Okay, so this seems like that will be my answer. All right, that right there, this is the function. that if you put in whatever year or time you want, tells you the population at that time. Okay? I got it from the function that tells you how fast the population's growing. All right, now let's pause for a minute and say, well, did this really do what I just said? Is this function such that if I took a year, a time, and put it in for x, that it would tell me the population at that time? Because that's what it's supposed to do. And I would say, well, it actually wouldn't, but only because it's incomplete. You see this plus c right there? That's the constant of integration. Anytime that we solve an indefinite integral or an antiderivative, anytime we solve a problem like this constant of integration shows up. Okay? And if you want the explanation on why it shows up, go back to the very first video that I made about U substitution. So there's this constant here, but what that number is not revealed in this process. Okay? We have to have more information. And the more information is this part. You see? This says the population in year 2 is 50,000. Okay, so I can put 2 for x, and it will tell me that the population is 50,000 people. And between those two pieces of information, I can find that number c. And then I'll know this function in its complete form. Okay? All right, so that part right here, this little bit of extra information, we're going to use that to find c, that constant of integration. Okay, now one more thing before I do that. We do have to be careful about the units here. So remember I said any number that's intended to measure something has units. It could be kilometers, it could be pounds, who knows, whatever it is. Okay, and here the population is given to be measured in millions. Okay, so if the number was 5, that would actually mean 5 million. Okay, so let's talk for a second about the conversion and how we'd have to work with that number. So here's something I'll reiterate real quick. So x is the number of people in millions. Okay, so we got to think of it that way. And so if you told me x is 5, that would mean 5 million. But I want to write it like this. I want you to see that we got the number and then we got the units. Okay? So if I say x is 5, that means 5 million. Let's say, well, there's the number is 5 and the units are 1 million people. And I actually wrote out the number intentionally. Okay? All right. Now, here's what we need to do. I need, in order for this function here to have that number be usable, I need it to be in millions. I don't need to say 50,000. I need to say a number in millions. Okay? I've got to preserve that unit. So here's what I'm curious about. I've got the number 50,000 people. Okay? So people is part of the unit. And I need to turn that into something, some number whose units are million people. All right? And that's the number I'm trying to figure out. So I wanted you to have that thought in your head that this is what I'm trying to do. I got this number and I need it to be like this. I need to know what that x is. So how do you think you could get that? Well, what if you took this million right here and you divided it over there? This one. Okay. And then that would allow you to solve for the x, this number that you're trying to figure out. Because right here, this has the proper units. This has the units that we're working with. So I do that, take 50,000, divide by million, I get 0.05. And then my equation says 0.05 people equals x people. That means that this number x that I was trying to find from the beginning has to be 0.05. Okay, so for you to say 50,000 people means that my number in that function is 0.05. Okay, so here we go. Let's use that to find c. Okay, so now I'm going to find that constant of integration c, and then this function will be complete. So it says in year 2, the population is 50,000 people. Now we know that that actually means 0.05 million people. Okay, so that's my population. And then I put over here that it said in year 2. So imagine if you put 2 for x and you squared it, you get 4, right? So I got -1/2 e to the -4 plus c, okay? Now, I said that if I only knew that number c, then this function would be complete. I would know everything I need to know about it in order to use it. So I just want to solve for c. So I'm looking at that. I'm saying, what's that? Okay. And I could calculate this number here with a calculator. I could take e to the -4 power and so on. You know, I could do that. But in my math lab, it doesn't call for us to do that. So I'm just going to leave it. I'm going to add this number to the other side, and it says c is 0.05 plus 1/2 e to the -4 power. So that's my number c. Okay. Now my final answer I'm going to put over here. P of x, the function that tells you the population at any time, is going to be -1/2 e to the -x squared plus c, but I find c to be this complex looking number over here. Nonetheless, it is what it is. Okay, it's 0.05 plus 1/2 e to the -4. So that will be my final answer for the question as desired to give a population function, a function that tells me the population at any time. Now that I know that number, I could compute that. If you gave me a time x in years, I put that number in with the help of a calculator. I'll calculate and it'll tell me what the population is. Okay, in millions, but it'll tell me the number. All right. So let's scratch this out. This is only my temporary final answer. Okay, we found C. There is my official final answer to part 1 of the question. Okay, now there's a secondary part to this question on my math lab, and it was this. As time goes on, what will happen to the population? So it might be that if this function can be trusted as a model of the population over time, then it might be the population grows bigger and bigger and bigger, okay? Or it might be that it stabilizes. It's, you know, but this question is asking about that. As time goes on, what will happen to the population? So let's do some interpreting here, because just looking at this function, it's like, it might be hard to tell. What does it mean to say as time goes on? So let's do this. Let's say that what that means in the terms of how a mathematician or a biologist might look at this is to say, well, like, we're just looking indefinitely into the future. What's going to happen, okay? So as x goes to infinity. So it's not like we have some like distant time in mind that's the end, but just as x goes to infinity means as time goes on, like as the years progress further and further and further indefinitely, okay? So we could think of it like that, just saying if this function tells me what the population is at any time, and what happens as time goes on, all right? What happens as x goes to infinity? So to answer this question, what we're doing is trying to figure out what's the limit as x goes to infinity as applied to this function, -1/2 e to the -x squared plus 0.05 plus 1/2 e to the -4 power. Okay, all right. Now, for me to calculate this limit, I noticed that there's only one part of this entire function that has anything to do with x going to infinity. So if x goes to infinity, it doesn't affect this number, 1/2 e to the -4 power. That is a number that is calculated. I don't know what this number is, but with a calculator, I can tell you it's just a number though. It's not a variable. It's not x, okay? And same thing with 0.05, all right? That's just a number. So the only where x appears is right here. And to help see what that is and how it's affected by x going to infinity, let's write it this way. Negative 1 over 2e to the x squared. Okay? All right, because that's what that negative exponent means. Now, we'll think about it like this. As x goes to infinity, then x squared gets bigger, right? So like if x was 10, 10 squared is 100. All right, if x is 15, 15 squared is 225. If x is 20, 20 squared is 400. Yeah, so as x goes to infinity means as x gets bigger and bigger and bigger, x squared also gets bigger and bigger and bigger. Now, keep that in mind, and also think about if I take e, a number which is about 2.7, and I raise that to powers that are bigger and bigger and bigger, then like that gets bigger and bigger and bigger, okay? All right, you take a number and you raise it to larger powers, you get larger results. So how we can think about this part then is it turns out to be like negative 1 over what turns out to be larger and larger and larger numbers, okay? And I'll just say like it's ultimately as x goes to infinity, it gets far enough out there, it's going to be negative 1 over a very large number, okay? And the larger number you divide by, the closer to 0 your result is going to be. That's just a property of arithmetic. The larger number you divide by, the smaller and closer to 0 your number is going to be. So what happens is as x goes to infinity, this part zeroes out of this entire formula. Okay? All right. So as time goes on, this element of my function disappears, is what we could say. And I'm left with this other stuff, 0.05 plus 1/2 e to the minus 4 power. Okay, so that's like your long run population. It's like I'll get that the population will stabilize. Okay, now I haven't calculated what that is, so I'm going to do that real quick. So 0.05 plus 1 over 2 e to the 4. Okay, so that turned out to be about, with some rounding, let's say 0.0591578 or so. Okay, so that's my long run population. It will stabilize at that number. And I think that on my math lab, the way this question is, it will ask you what the long run population is. Okay, now remember, this number is in millions. Okay, remember we talked about the units before? Okay, so here's my long run population, stabilizing at that number. My units are in millions of people. So what if we just wanted to give the number though? In math and economists and biologists, they often like include the number million in the units so that we're not working with numbers quite as gigantic. But what if we just want to tell somebody, here's the long run stable population. This is the population going in this direction. Then we might tell them like 59,000 or something. So I'm going to take this and I'm going to multiply it by 1,000,000, and I'm going to give the number that way. Okay, so that turns out to be this 59,000. Okay, 157, or I'm going to round it to the nearest person. I get 157.8. Okay. All right, so in the long run, my population will stabilize to a little less than 60,000 people. Exact number 59,158, rounded to the nearest person. Okay. All right. Now, I hope that the limit didn't catch too much off guard. We haven't talked about limits in a while, but if we can at least see this, that even with a calculator, you can see what happens to this. Put in 10 into that. See how close to 0 it is. Then maybe put in 20. See how much closer to 0 it is. If you didn't follow my discussion about how this number in the denominator turns out to be very large And so the quotient practically 0. Put in some numbers that get bigger and bigger and bigger, and you'll get to see that trend, all right? Anyway, okay, so that's both parts of this one. The way that you'll see it on my math lab. I make this video right now. Somebody happened to ask about it. So I thought it'd be good to have a video about it. But that's true for any other question that you see, that you run into, that you need help with. Always ask me. I can make the video to help you out.